So now that we've talked about Taylor polynomials and this idea of estimating values using them, the question may be, how far away from the center can I actually go and still get an actual estimation? And this is the idea that we're going to look at now. While we've been dealing with Taylor polynomials as a finite polynomial, I'm now going to expand the idea to series and the idea of the power series and trying to see when it converges. So the set of all the values of x for which a power series actually converges is known as the interval of convergence. Very much related to this is the idea of the radius of convergence, which is the distance from the center to the boundary of the interval of convergence. And so this is going to be our ultimate goal here, is I want to be able to find my interval of convergence and the radius of convergence. So how do we do that? I'm going to start by using my ratio test, and this will give me some kind of window. The ratio test says that it converges whenever the ratio is less than 1. So that's what I'm going to do. I'm going to set up this ratio and try to figure out when it's less than 1. The ratio test is inconclusive whenever it's equal to 1, though. So I'm going to have to test my endpoints separately using other techniques. So let's look at some examples of this in action. I'm going to start with the series, the summation of xk over k factorial. So I want to use my ratio test. For my ratio test, I need to consider the limit as k goes to infinity of the absolute value of ak plus 1 over ak. So here I have the limit of k goes to infinity of the absolute value. The top of the fraction changes all the k's to k plus 1, so I have x to the k plus 1 over k plus 1 factorial, over my original a sub k, x to the k over k factorial. Remembering that division by fractions means multiply by the reciprocal, I have that this is the limit as k goes to infinity of the absolute value, x to the k plus 1 over k plus 1 factorial times k factorial over x to the k. We then need to start simplifying. So I'm going to start with the x terms. The top of the fraction has an x to the k plus 1 and the bottom has an x to the k. Using my rules for exponents, I'm going to get that that reduces to a single x on the top of the fraction. I then have a k factorial on the top and a k plus 1 factorial on the denominator. And if you expand these out and cancel appropriately, you get that that just leaves a k plus 1 on the denominator. I now actually want to evaluate the limit. So it's important here to realize that x is a set number. It's not changing right now. K is what we're taking the limit of. So we have x over a really, really big number when we take this limit. And anything over a really, really, really big number is going to approach 0. So this limit is 0. Our ratio test says that as long as this limit is greater than or equal to 0 and less than 1, the series converges. So what I'm looking for here is what values of x make this limit less than 1. Well, that's all values of x. 0 is always less than 1. It doesn't matter what we pick x to be, this will still be less than 1. Since this always works, my interval of convergence is negative infinity to infinity, and the radius would just be infinity. Let's look at another one. This time I have the sum of negative 1 to the k, x minus 2 to the k, all over 4 to the k. And once again, I'm going to start with my ratio test. That tells me I want to look at the limit as k goes to infinity of the absolute value of. The top of the fraction should be a sub k plus 1. So I'm going to take this and change all of my k's to k plus 1. The bottom half of the fraction is just a sub k. It's what I originally had in my series. I can now start to look at simplifying. So remembering that dividing by a fraction is multiplying by the reciprocal. So now I have the limit as k goes to infinity of negative 1 to the k plus 1, x minus 2 over k plus 1, divided by 4 to the k plus 1, all times 4 to the k over negative 1 to the k, x minus 2 to the k. So let's start simplifying this. The first thing I'm going to notice is the negative 1 to the k plus 1 and the negative 1 to the k. All those are really doing is changing my signs back and forth between positive and negative. But I'm taking the absolute value anyway, so they don't really matter. So I'm going to completely ignore the negative ones. I'm then going to look at the x minus 2's. I have k plus 1 on the top and a k on the bottom. So using my properties of exponents, I get an x minus 2 on the top. For the 4's, I have 4 to the k on the top and 4 to the k plus 1 on the bottom. Once again, using my properties of exponents, I'm left with a single 4 on the denominator. I want to take the limit as k goes to infinity, but there are no k's here. So the limit is just x minus 2 over 4 inside of absolute values. My ratio test says that this converges whenever this limit is less than 1. So I need to know when the absolute value of x minus 2 over 4 is less than 1. Using properties of solving absolute value inequalities, I can rewrite this as negative 1 less than x minus 2 over 4 less than 1. I can then multiply everything by 4. I then add 2 to all three sides. And I get negative 2 is less than x is less than 6. So my interval of convergence does tell me that it converges between negative 2 and 6. The question is, do I include negative 2 or 6? The ratio test is inconclusive when it's actually equal to 0, so I'm going to have to use other methods. Let's start with x equal to negative 2. If I stick in negative 2 in for x, this series becomes the summation of negative 1 to the k times negative 4 to the k over 4 to the k. Using the fact that negative 4 is negative 1 times 4, and then properties of exponents, I can rewrite this as negative 1 to the k times negative 1 to the k times 4 to the k over 4 to the k, which is then the summation of negative 1 to the 2k. My 4k's cancel, and I have 2 negative 1 to the k's. Well, negative 1 to the 2k is just always going to be 1. So this is the summation of just 1. So essentially 1 plus 1 plus 1 plus 1 plus 1 forever and ever and ever. So we know this diverges. So we do not include negative 2. Now let's check 6. Sticking 6 in for x in my original series gives me the summation of negative 1 to the k times 4 to the k over 4 to the k. My 4 to the k's cancel, and that just leaves me with the series, the summation of negative 1 to the k. So essentially I'm going to have 1 minus 1 plus 1 minus 1 plus 1 minus 1 forever, which once again doesn't converge. It's just going to oscillate between 0 and 1. So we do not include either of these. I then have that my interval is negative 2 to 6 with parentheses since we don't include either one of them. And r is equal to 4. The center of this interval is 2. And the distance between 2 and 6 is 4. The distance between negative 2 and 2 is 4. To find the radius, it may be more helpful to think of it in terms of the diameter. The distance between negative 2 to 6 is 8, so that would be our diameter. So the radius needs to be half of that, or 4. Let's look at some more. This time I'm going to consider k factorial times x to the k. My ratio test then says I need the limit as k goes to infinity of k plus 1 factorial times x to the k plus 1 divided by k factorial x to the k. Let's start simplifying. A k plus 1 factorial divided by k factorial just leaves us with a k plus 1. X to the k plus 1 over x to the k is just x. So now I have the limit as k goes to infinity of the absolute value of k plus 1 times x. Once again, we're going to treat x just like a number. We're taking the limit as k goes to infinity. And as k goes to infinity, k plus 1 also goes to infinity. And then infinity times x is still going to be infinity. So the ratio test wants to know when this limit is less than 1, which it's never less than 1. With one exception, which is x equal to 0. If x is equal to 0, then we're just looking at the summation of 0, which would converge. So my interval is just x equal to 0. And then the radius would be 0. So these three examples that I've done so far do represent the three cases. I could get that it always converges, like my first case. I could get an actual interval where it converges, like my second case. Or I could get that it only converges at a single point, like my third case.